May 15, 1945. A bombed German aircraft factory outside Munich. The engineering report from visiting Allied inspectors would never fully capture what they discovered in the twisted wreckage that morning. German fighter planes that weren't assembled like American aircraft, they were forged. Single-piece magnesium wings pressed by hydraulic machines, generating 33,000 tons of crushing force. Through the smoke and rubble of the destroyed facility, massive steel press columns lay toppled like fallen monuments to engineering that American experts had never imagined possible. No riveted joints, no welded seams, no assembly lines full of workers connecting hundreds of small parts. The Germans had been building aircraft like sculptures, shaped from solid metal blocks under pressures that defied American manufacturing wisdom. In American factories, engineers insisted that presses larger than 18,000 tons were impractical. The hydraulic systems too complex, the steel castings too massive to control. Most believed 30,000 tons represented the absolute ceiling of mechanical possibility. The Germans had exceeded that ceiling and planned machines nearly twice as large. 8,000 miles from the ruins of Munich, American military planners faced an impossible choice: build presses that European experts claimed would destroy themselves, or accept permanent technological defeat. Lieutenant General Kenneth B. Wolfe stood in the wreckage of the Messerschmitt facility, his engineering background allowing him to read the destruction like a technical manual written in twisted steel and shattered concrete. The massive hydraulic press that had dominated the factory floor now lay in sections, its 33,000-ton capacity evident even in ruin. What struck him wasn't the scale of German ambition, but the methodical precision with which they had achieved the impossible. Each wing component for the Me-262 jet fighter had been shaped from solid aluminum billets under pressures that American metallurgists insisted would fracture any hydraulic system ever designed. The implications crystallized as Wolfe examined the press specifications scattered among the debris. German engineers hadn't just built larger machines, they had fundamentally reimagined aircraft manufacturing. Where American factories employed hundreds of workers riveting thousands of individual pieces into wing assemblies, the Germans had reduced entire wing sections to single hydraulic operations lasting less than 30 minutes. The structural advantages were undeniable. Forged components eliminated stress concentrations at rivet joints, reduced weight by eliminating overlapping materials, and created strength characteristics that welded assemblies could never match. More troubling, German records indicated plans for presses generating 55,000 tons of force, machines that would make their current achievement seem conservative. Within 18 months, American intelligence confirmed Soviet engineers had dismantled the Munich facility piece by piece, shipping the 33,000-ton press and all associated blueprints to manufacturing centers beyond the Urals. The technical specifications that Wolfe had studied in bombed German factories were now serving Stalin's aircraft designers. By 1947, Soviet jet prototypes were appearing over Eastern European airspace with single-piece wing structures that American engineers recognized as German-influenced design. The Cold War had inherited World War II's unfinished technological revolution. The crisis deepened when American aircraft manufacturers began designing jets for speeds approaching twice the speed of sound. Traditional riveted wing construction created vibration patterns and stress concentrations that could tear aircraft apart at supersonic velocities. Boeing engineers calculated that their experimental B-52 bomber required wing spars machined from solid aluminum billets weighing 8 tons each, components far beyond the capacity of any American press. Convair's supersonic fighter prototypes demanded wing roots forged under pressures exceeding 40,000 tons. The specifications weren't theoretical exercises, they were operational requirements for aircraft that would determine American air superiority against Soviet jet development. European metallurgical experts, led by voices like Dr. Heinrich Brenner, maintained their long-standing position that hydraulic systems above 30,000 tons represented fundamental engineering impossibilities. Brenner's calculations, widely respected throughout American technical circles, demonstrated that larger presses would suffer catastrophic hydraulic failures due to uncontrollable pressure fluctuations and materials, science limitations that no amount of American engineering enthusiasm could overcome. His correspondence with Air Force planners consistently emphasized that German press development had pushed hydraulic technology to its absolute limits, and Soviet attempts to exceed those limits would likely result in spectacular industrial disasters rather than manufacturing breakthroughs. The theoretical debate became urgent reality in 1949 when Korean conflict demonstrated Soviet jet capabilities that surpassed American expectations. MiG-15 fighters were outclimbing American F-86 Sabres and displaying structural integrity under combat loads that suggested advanced manufacturing techniques. Intelligence reports confirmed Soviet aircraft components were being produced using captured German press technology, giving Russian designers advantages that American manufacturers couldn't match with existing equipment. The technical gap wasn't closing, it was expanding in favor of American adversaries. Wolf's response was characteristically direct. Rather than accepting European limitations, he approached the challenge like a military campaign, requiring unprecedented industrial mobilization. The heavy press program emerged from Air Force planning sessions as America's most ambitious manufacturing initiative since wartime production programs. The specifications were deliberately audacious: 10 presses ranging from 18,000 to 50,000 tons of capacity, distributed among American aircraft manufacturers to ensure no single facility represented a strategic vulnerability. The timeline was equally aggressive: full operational capability within 6 years. The Air Force delegation that arrived at Mesta Machine Company's West Homestead facility in October 1949 represented American industrial ambition confronting established engineering wisdom. Mesta President Lawrence Iverson listened as military planners outlined press specifications that exceeded anything his company had ever attempted. The largest casting Mesta had ever poured weighed 120 tons. The proposed 50,000-ton press required individual steel components weighing 350 tons each. The hydraulic systems demanded pressures that would challenge the strongest steel alloys available. The assembly process would require construction techniques that hadn't been tested at such massive scales. Iverson's initial response reflected decades of engineering conservatism that had built Mesta's reputation for reliable industrial machinery. The company had supplied steel mills with equipment that operated for decades without major failures, but such reliability was achieved through proven design principles and tested materials. The Air Force specifications pushed beyond proven limits into territories where failure could mean catastrophic destruction of equipment worth millions of dollars. European experts had established theoretical boundaries for hydraulic press development based on sound metallurgical principles and centuries of mechanical engineering experience. Yet Iverson recognized that conventional wisdom was colliding with national necessity. Soviet capabilities were advancing while American aircraft manufacturers struggled with technological limitations that enemy engineers had already overcome. The choice wasn't between safe engineering and risky innovation. It was between accepting permanent technological disadvantage or attempting achievements that would restore American industrial supremacy. The heavy press program represented America's commitment to engineering excellence over European caution, industrial ambition over established limitations. The decision to proceed came not from confidence in success, but from recognition that failure to attempt the impossible meant accepting defeat by adversaries who had already achieved it. Mesta Machine Company's West Homestead foundry had built its reputation on the impossible, but the specifications spread across Lawrence Iverson's desk represented challenges that exceeded even Carnegie Steel's most ambitious projects. The proposed 50,000-ton press demanded steel castings larger than locomotives, hydraulic cylinders 14 feet in diameter, and supporting columns 76 feet tall that would remain straight under loads equivalent to the weight of an entire steel mill. Iverson walked the foundry floor where his crews had poured the largest industrial castings in America for 50 years, calculating whether existing furnaces could even melt enough steel to create single pours weighing 350 tons. The engineering mathematics were unforgiving. A 50,000-ton press required 8 massive steel columns, each 40 inches in diameter and machined to tolerances measured in fractions of inches. The hydraulic system demanded water pressurized to 7,000 pounds per square inch, pressures that would rupture conventional piping like overinflated balloons. The foundation alone required a concrete pier extending 30 feet into Cleveland bedrock with steel reinforcement patterns that would consume more metal than most buildings. Traditional European approaches emphasized incremental improvements to proven designs, but American specifications called for engineering leaps that multiplied every technical challenge by factors of 10. Alexander Zeitlin's hydraulic calculations revealed the true scope of the challenge. The press would require 23 major control valves, some weighing 12 tons each, and machined to tolerances that demanded custom-built equipment to manufacture. Water flow capacity of 26,438 gallons per minute meant the hydraulic system could drain a swimming pool in seconds and fill a house basement in under 2 minutes. The pressurization chamber required steel walls 8 inches thick to contain forces that could launch the hydraulic ram through the factory roof if containment systems failed. European engineers had established 30,000-ton limits precisely because larger systems generated hydraulic pressures that exceeded the structural capabilities of any steel alloy then available. Iverson's response demonstrated the fundamental difference between American and European engineering philosophy. Where European designers built to proven specifications with established safety margins, American engineers embraced over-engineering as a design principle. If hydraulic pressures threatened steel containment, American designers would use steel twice as thick as calculations required. If casting tolerances approached materials science limits, American foundries would develop new techniques that exceeded those limits by comfortable margins. The approach wasn't reckless, it was systematic application of engineering overkill to ensure success under conditions that had never been tested. The casting challenge became Mesta's first technical breakthrough. Pouring 350 tons of molten steel required furnace temperatures of 3,000 degrees Fahrenheit and cooling strategies that controlled solidification across masses that dwarfed anything previously attempted. Traditional casting techniques relied on predictable cooling patterns for objects weighing less than 50 tons. 350-ton castings created thermal dynamics that could produce internal stresses capable of cracking steel columns like glass figurines. Mike Kowalski's foundry crews developed custom pouring procedures that staged molten steel delivery through multiple furnaces, controlling cooling rates across massive steel volumes with precision that metallurgists had declared impossible. The breakthrough came through American willingness to attempt techniques that European foundries considered too risky. Kowalski's workers constructed specialized molds that controlled cooling through calculated placement of steel chills and insulating materials, creating predictable thermal gradients across castings larger than railroad engines. The process required 12-hour shifts where foundry workers monitored molten steel behavior with timing measured in minutes. Delays of even 30 minutes could result in cooling patterns that would ruin months of preparation and waste tons of premium steel alloys. Transportation presented equally unprecedented challenges. Moving 350-ton steel castings from Pittsburgh foundries to Cleveland assembly sites required custom railroad cars designed specifically for loads that exceeded the capacity of any existing freight equipment. The railroad cars themselves became engineering projects, with reinforced frames and specialized bearing systems that could support weights equivalent to loaded locomotives. Routes had to be surveyed to ensure bridge capacities could handle the concentrated loads, and railway officials required structural analyses proving that track systems wouldn't be damaged by repeated passage of equipment carrying unprecedented weights. The precision requirements bordered on the absurd. 76-foot steel columns had to be machined straight within tolerances of less than 1 inch over their entire length, specifications that required custom-built lathes with beds longer than most factory buildings. The column threading demanded nuts weighing 55 tons each, machined with precision that would allow threaded connections to support millions of pounds of force without mechanical failure. Mesta's machine shops developed threading techniques for steel components so large that conventional measurement tools couldn't span their dimensions. By early 1951, Mesta foundries were successfully pouring steel castings that exceeded European size limitations by factors of 3. The metallurgical analysis revealed steel grain structures superior to smaller welded assemblies, proving that American over-engineering had achieved not just unprecedented size, but superior material quality. The first 350-ton casting emerged from cooling molds with internal structure, uniformity that surpassed European predictions for maximum achievable quality in large steel components. European experts had been wrong about the fundamental limitations of large-scale steel casting, but Mesta's success represented only the first phase of challenges that would determine whether American industrial ambition could transform theoretical specifications into operational machinery capable of reshaping global manufacturing capabilities. The physics of cooling 350 tons of molten steel threatened to invalidate every theoretical breakthrough Mesta had achieved. Steel contracts as it solidifies, and the shrinkage rates across massive castings created internal stresses that could crack even perfectly poured components during the cooling process. Traditional foundry wisdom held that castings above 50 tons required sectional pouring techniques that assembled multiple smaller pieces through welding or mechanical connections. The alternative, attempting to control thermal dynamics across steel volumes equivalent to small buildings, had never been successfully demonstrated at any foundry in industrial history. Mike Kowalski understood the metallurgical realities better than most engineers with advanced degrees. 30 years of pouring large castings had taught him to read molten steel behavior through subtle changes in color, flow patterns, and surface characteristics that indicated internal temperature variations invisible to instruments. 350-ton pours created thermal gradients that extended beyond his experience, but Kowalski recognized that success would depend on foundry workers developing intuitive understanding of steel behavior at scales where miscalculations would waste months of preparation and tons of premium alloy materials. The custom furnace systems represented American engineering's response to limitations that European foundries had accepted as permanent. Mesta constructed multiple interconnected furnaces capable of maintaining molten steel at precisely controlled temperatures while coordinating simultaneous pours that filled massive molds through carefully timed sequences. The furnaces themselves required steel-lined chambers that could withstand 3,000-degree temperatures for hours without degradation, and fuel systems that delivered heat with consistency that varied less than 50 degrees across the entire pouring operation. Kowalski's crews developed pouring choreography that resembled military precision more than traditional foundry work. Each 350-ton casting required coordination between 12 foundry workers operating furnace controls, mold preparation, and molten steel delivery systems with timing measured in seconds. The molten steel had to flow through ladles weighing 20 tons when empty, guided through pouring channels that distributed metal evenly across mold cavities larger than most factory floors. Temperature monitoring required constant measurement at dozens of points, and cooling control demanded placement of steel chills and insulating materials according to calculations that predicted thermal behavior across unprecedented steel masses. The first major casting attempt in March 1952 demonstrated both the promise and peril of pushing foundry techniques beyond established limits. The pour itself proceeded flawlessly. Molten steel filled the mold cavities with uniformity that suggested perfect temperature control and flow distribution. The 6-week cooling period that followed became an exercise in metallurgical suspense, as Mesta engineers monitored internal temperatures and calculated stress patterns that would determine whether months of preparation had produced usable steel or expensive scrap metal. European experts had predicted that thermal stresses would create internal fractures that would render large castings structurally worthless, regardless of external appearance. The breakthrough came not through theoretical calculations, but through practical innovations that emerged from foundry floor experience. Kowalski's workers discovered that controlled placement of steel chills, metallic inserts that accelerated cooling in specific locations, could create predictable thermal gradients that guided shrinkage patterns throughout massive castings. The technique required understanding how steel would contract during solidification and positioning cooling controls to ensure uniform stress distribution across components weighing more than loaded freight trains. Transportation logistics became engineering challenges that matched the complexity of the casting process itself. Moving 350-ton steel components from Pittsburgh foundries to Cleveland assembly sites required custom railroad equipment designed specifically for loads that exceeded conventional freight capacity. The specially built railroad cars featured reinforced frames with 64 wheels distributed across extended wheelbase configurations that spread concentrated weights across longer sections of track. Bridge inspections along transportation routes revealed that several railroad spans required structural reinforcement to handle repeated passage of equipment carrying unprecedented loads. The machining requirements pushed American manufacturing capabilities toward their absolute limits. Finishing 76-foot steel columns demanded custom-built lathes with beds extending across entire factory buildings and cutting tools capable of maintaining precision tolerances across steel components longer than most city blocks. The 96-inch lathes represented manufacturing equipment that existed nowhere else in global industry, designed specifically to meet specifications that no other project had ever required. Tool wear became a critical concern, as cutting implements that could machine steel of this scale and hardness represented specialized equipment that couldn't be easily replaced if damaged during operations. Quality control presented challenges that exceeded existing metallurgical testing capabilities. Conventional steel analysis techniques worked effectively on samples, representing small fractions of total casting volume, but 350-ton components required testing methods that could evaluate internal structure throughout steel masses too large for traditional inspection procedures. Mesta developed ultrasonic testing techniques that could detect internal flaws across steel sections thick enough to stop bullets, ensuring that completed castings possess structural integrity throughout their entire volume rather than just at accessible surfaces. The validation moment came in late 1952, when metallurgical analysis of the first completed 350-ton casting revealed steel grain structure superior to anything achieved through welded assembly techniques. The uniform cooling had created internal crystalline patterns that distributed stress more effectively than traditional construction methods, proving that American over-engineering had achieved not just unprecedented size, but superior material performance. The steel quality exceeded European predictions for maximum achievable strength in large components, demonstrating that systematic application of American manufacturing philosophy could surpass established metallurgical limitations through disciplined technical innovation rather than theoretical breakthroughs. European foundries had been constrained by conservative approaches that avoided risks inherent in pushing beyond proven limits, but American success proved that controlled application of extreme techniques could achieve results that theoretical analysis had suggested were impossible. The completed steel castings arriving in Cleveland presented Alexander Zeitlin with an engineering paradox that threatened to invalidate years of technical breakthrough. How do you assemble an 8,000-ton machine when the largest available crane can lift only 200 tons? Traditional assembly methods relied on overhead lifting equipment that could position components with precision, but the press columns alone weighed 350 tons each, nearly twice the capacity of the most powerful mobile cranes in American industrial inventory. European assembly techniques assumed that large machinery could be built through sequential installation of manageable components, but the 50,000-ton press demanded assembly methods that had never been attempted at such massive scales. Zeitlin's solution demonstrated American engineering's willingness to abandon conventional approaches when conventional methods proved inadequate. Rather than seeking more powerful external lifting equipment, Mesta engineers designed the press to assemble itself through hydraulic systems built into the structure's foundation. Temporary hydraulic jacks embedded in the concrete pier could generate lifting forces that exceeded any crane capacity, positioning steel components through controlled hydraulic pressure applied from below rather than overhead support systems. The technique required extraordinary precision in foundation preparation, as hydraulic lifting points had to be positioned with accuracy that would allow proper alignment of components weighing more than loaded locomotives. The foundation work began in Cleveland during winter months of 1953, requiring concrete pours in sub-freezing temperatures that challenged every aspect of conventional construction practice. The 30-foot deep concrete pier extended through Cleveland's clay soil into bedrock formations that could support concentrated loads exceeding the weight of entire factory buildings. Steel reinforcement patterns within the concrete required more metal than most bridge construction projects, with reinforcing bars positioned to distribute hydraulic lifting forces throughout the foundation structure. The concrete mixing required specialized techniques that prevented freezing during winter pours, while maintaining strength characteristics necessary to support unprecedented mechanical loads. Column installation represented the most dramatic phase of assembly operations. The 76-foot steel posts arrived in Cleveland as precisely machined sections that would be threaded together using nuts weighing 55 tons each. The threading operation required hydraulic equipment capable of rotating nuts larger than automobile engines, while maintaining alignment tolerances measured in fractions of inches across connections that would support millions of pounds of operational force. Traditional threading techniques relied on manual alignment and gradual tightening, but 55-ton nuts demanded hydraulic rotation systems that could apply torque forces beyond the capacity of any conventional industrial equipment. The hydraulic system installation pushed American manufacturing precision toward absolute limits of achievable accuracy. 23 major control valves, some weighing 12 tons each, had to be positioned and connected through hydraulic lines that could withstand 7,000 pound per square inch pressures without leakage or failure. The valve positioning required spatial accuracy that allowed proper hydraulic flow through systems designed to move 26,438 gallons of water per minute, flow rates sufficient to drain industrial reservoirs in minutes and capable of generating hydraulic forces that could crush conventional piping like paper tubes. Assembly precision became an exercise in mechanical perfection that exceeded tolerances achieved in watch manufacturing. Despite working with steel components weighing hundreds of tons, Mesta assembly crews maintained dimensional accuracy within fractions of inches across connections spanning the height of 20-story buildings. The column alignment required surveying, techniques borrowed from bridge construction, with measurements verified through optical instruments that could detect positional variations invisible to conventional inspection methods. Each threaded connection had to achieve perfect concentricity to ensure that operational loads would be distributed evenly throughout the press structure rather than concentrated at stress points that could cause catastrophic failure. The hydraulic control systems represented technological achievements that surpassed European hydraulic engineering by generations. Water pressurization to 7,000 pounds per square inch required pumping equipment that could maintain pressure consistency across hydraulic circuits extending throughout the entire press structure. The pressure regulation demanded control valves that could modulate massive hydraulic flows with precision that varied less than 50 pounds per square inch across operational cycles lasting several minutes. Hydraulic fluid contamination became a critical concern, as particles that would be insignificant in conventional machinery could cause valve failures that would disable equipment worth millions of dollars. By spring 1955, the completed press dominated Cleveland's industrial landscape like a mechanical cathedral designed for purposes that transcended conventional manufacturing. The structure rose 285 feet from foundation to peak, with 118 feet extending below ground level into bedrock formations that anchored the entire assembly against forces that could shift buildings. The visible portion suggested only half the engineering achievement, as foundation systems and hydraulic equipment represented technical complexity that matched the dramatic scale of above-ground components. The moment of verification arrived on May 5, 1955, when Mesta engineers initiated the first operational test of hydraulic systems designed to generate 50 million pounds of crushing force. The pressurization sequence began with water pumps gradually building pressure throughout hydraulic circuits that extended through every major component of the press structure. The massive ram descended with mechanical precision that compressed a test block of aluminum into geometric perfection that demonstrated force distribution accuracy exceeding theoretical calculations. 50 million pounds of pressure applied through hydraulic systems that had never been tested at such scale achieved results that validated years of engineering innovation and proved that American industrial ambition could transform unprecedented technical specifications into operational machinery that surpassed every prediction of European engineering limitations. The euphoria of successful initial testing lasted exactly 6 months. In November 1955, routine inspection of the Cleveland press revealed hairline fractures in 2 of the massive supporting columns, cracks that propagated along stress lines exactly where Dr. Heinrich Brenner's calculations had predicted catastrophic failure would begin. The fractures appeared as thin, dark lines in steel that had been engineered to withstand forces beyond any previous mechanical application, but the evidence was undeniable. European experts had been correct about fundamental limitations that American over-engineering couldn't overcome through brute force approaches to materials science. Alexander Zeitlin studied the crack patterns with the methodical precision that had guided every phase of press development, recognizing that the failures followed predictable stress concentrations that occurred when 50 million pounds of force compressed through steel columns operating at the absolute limits of metallurgical capability. The cracks weren't random material failures. They represented systematic responses to operational stresses that exceeded the long-term endurance capabilities of steel alloys, subjected to repeated loading cycles. European engineering wisdom had established 30,000-ton limitations precisely because larger systems generated stress patterns that would eventually compromise structural integrity regardless of initial material quality. The crisis threatened to validate decades of European skepticism about American industrial ambition exceeding practical engineering boundaries. Brenner's correspondence with American technical committees had consistently warned that hydraulic systems above proven capacity limits would suffer exactly these types of progressive failures, arguing that initial operational success meant nothing if equipment couldn't sustain performance over extended operational periods. The hairline cracks represented the beginning of structural degradation that could culminate in catastrophic collapse if the press continued operating at full capacity, potentially destroying millions of dollars of equipment and invalidating the entire heavy press program. Conventional engineering responses would have demanded immediate capacity reductions to prevent progressive crack propagation, but Zeitlin recognized that reducing press capabilities would eliminate the strategic advantages that justified the entire development effort. Aircraft manufacturers needed components forged under maximum pressure to achieve structural characteristics that conventional manufacturing methods couldn't duplicate. Reducing operational capacity meant accepting permanent technological disadvantage against Soviet capabilities that had already demonstrated superior aircraft performance through advanced forging techniques. American strategic interests required solutions that maintained full press capability while addressing structural concerns that European experts had correctly predicted. Mesta's engineering response demonstrated fundamental differences between American and European approaches to technical challenges that threatened established projects. Rather than accepting operational limitations imposed by materials science constraints, American engineers developed new metallurgical techniques that addressed stress concentration problems through innovative heat treatment processes that had never been applied to steel components of such massive scale. The heat treatment procedures required controlled heating and cooling cycles that could modify steel grain structure throughout 350-ton castings, relieving internal stresses that had accumulated during operational loading without compromising the fundamental strength characteristics that enabled 50,000-ton pressing capacity. The stress relief techniques pushed metallurgical science into territories that European foundries had never explored, heating steel columns to temperatures approaching 2,000 degrees Fahrenheit and controlling cooling rates across components weighing more than locomotives required furnace equipment that could maintain precise temperature distribution throughout steel masses that exceeded the capacity of conventional heat treatment facilities. The process demanded understanding of thermal dynamics at scales where traditional metallurgical principles had never been tested, and cooling control that could modify internal stress patterns without creating new weaknesses that would compromise operational integrity. Zeitlin's breakthrough came through recognition that the cracks represented predictable responses to operational stress patterns that could be managed rather than eliminated. American engineers developed new hydraulic control systems that varied pressure application throughout the pressing stroke, reducing peak stress concentrations while maintaining the maximum force necessary for aircraft component forging. The variable pressure systems required hydraulic controls that could modulate 50 million pounds of force with precision that prevented stress spikes while ensuring adequate pressure for metallurgical transformation of aluminum and steel workpieces. The hydraulic innovation represented technological advancement that exceeded European hydraulic engineering capabilities by decades. The new control systems could sense workpiece resistance during pressing operations and automatically adjust pressure application to minimize structural stresses while achieving optimal material forming. The technology required pressure sensors that could detect force variations across ranges that extended from 0 to 50 million pounds, and hydraulic valves that could respond to sensor feedback with adjustments measured in pounds per square inch across systems handling pressures that could crush conventional equipment instantaneously. Implementation of the new systems required modifications to all 10 heavy press program machines during 1956, transforming each press into equipment that exceeded original specifications through technological improvements that emerged from operational experience rather than theoretical design work. The modifications proved that American engineering philosophy could respond to technical challenges through innovation that enhanced rather than compromised original capabilities. European approaches would have demanded design changes that reduced operational capacity to prevent structural problems. But American solutions maintained maximum capability while addressing the underlying causes of stress concentration through systematic engineering improvements. By late 1956, all 10 heavy press program machines were operational with enhanced hydraulic systems that eliminated stress concentration problems while maintaining full 50,000-ton capacity. American aircraft manufacturers were producing single-piece wing spars and structural components that Soviet engineers couldn't duplicate using captured German technology, proving that American industrial innovation had achieved strategic advantages that justified years of technical development effort. The press operations were forging aluminum and steel components with precision and strength characteristics that exceeded European manufacturing capabilities by margins that couldn't be overcome through incremental improvements to conventional techniques. The vindication was complete. American engineering had not only achieved unprecedented manufacturing capability, but had solved operational challenges through innovations that exceeded original design specifications, demonstrating industrial competence that surpassed European theoretical limitations through practical solutions that emerged from systematic problem solving rather than acceptance of established constraints.